Hi, welcome to another lecture on business mathematics. Today we are going to continue our conversation about powers, parentheses, polynomials, and optimal boxes. This is going to be part 2 of the discussion. So last time we talked about powers, like x squared, x cubed, x to the 4, and the rules for that. Today we are going to continue with the issue of parentheses and polynomials. Let's just go back and take a look at what we did yesterday. We had this rules of exponents. So we said, excuse me, if you are operating with the same basis, so here I have product of two powers with the same base. I add the exponent. If I'm dividing them, I subtract the exponents. If I have double exponentiation, then I multiply the exponents. A result of this was that a number raised to the power of 0 is 1, and raised to a negative exponent, it means 1 over same base to positive exponent. Then we talked about having different bases and the rules for that. Now we are going to go after the issue of order of operation and the role of parentheses. So in mathematics, as in life, the order you are to carry out certain operations makes all the difference. In a very simple setting, when you want to step out of a room, you open the door and then you step outside. If you try to do this thing in reverse order, that is, step outside and then open the door perhaps, well, that becomes a scene for a sitcom or something like that. Well, in life sometimes it's clear in which order you're supposed to do something, but in mathematics it's not so clear, and we have to come up with a convention. And parentheses is a way of actually establishing a particular order. So let's go and start this topic. So we want to make a distinguishing remarks that's going to help us tell the difference between these situations. So you see in the second set of these expressions we have a parentheses, and in the first one we don't. And the results are substantially different. So what does parentheses do? So let's go back to our algebra. So what is the role of a parentheses? Parentheses, well, as you see in mathematics, it is written as these two curved brackets. Sometimes other notations get to be used, like square brackets, sometimes curly brackets, sometimes angle brackets, but this is the most common that we see. By the way, in English language too, the idea of parentheses exists. So sometimes they just use the same notation, and sometimes they just use two dashes. So a parenthetical remark would be a sentence in the middle of another one, and the same issue comes up there. Now let's go ahead and take a look at the mathematical side of this thing to see what is the discussion all about. Suppose I write 5 plus 4 times 3. How do we understand this? Well, there are two ways of interpreting this thing. One is to say that I add the 5 and 4 first, and then I multiply by 3. And the other one is to say I multiply 4 and 3 first, and then add 5. So in either way, that parentheses tells us what to do first. So parentheses creates an order of operation of its own, so it dictates to us that we have to take care of inside the parentheses first before we enter anything outside of it. Well, what if the parentheses weren't there? What would happen then? Well, all mathematics books, mathematics calculators and so on, they agree on the following, that the multiplication comes first and then addition comes later. But I've seen some old style calculators that as soon as you type 5 plus 4 times, it already converts 5 plus 4 to a 9. It doesn't wait to see what you're going to do later on, and then goes ahead and multiplies that by 3. So it's possible in some business application or old style business calculators, this might translate to that. But in all mathematics texts, we have a particular order in mind. The particular order says you at the top of the pole is a parentheses, after that is the power, after that is multiplication and division, after that is addition and subtraction. So typically students memorize this thing by saying, well, P for parentheses, E for exponentiation, M for multiplication, D for division, A for addition, and S for subtraction. And then they memorize that the order is PEMDAS, or however you pronounce it. So that's the established order in mathematics. So if we didn't have a parenthesis here, we would understand automatically that this is what is meant. If we wanted to add 5 and 4 first, then we are forced in using the parentheses to dictate that that is going to be done first and the multiplication is going to come later. Okay, same issue comes up all over the place, so let's go ahead and practice these things. So suppose I write 2x in parentheses raised to power of 4. What does that mean? This means multiplication is happening first and this exponentiation happens next. So parentheses always important when there are two operations to be carried out and we want to figure out what goes first. So 2x is calculated and raised to power of 4 simply means 2x times 2x times 2x times 2x, and of course now 2 times 2 times 2 times 2, that is 2 to the power of 4 and then x to power of 4. Or if you want to expand it more, 16x to power of 4. As opposed to what? As opposed to if I had written 2x4, what do we understand here? So exponentiation beats multiplication. So this is understood as the following: 2 times x to power of 4. So exponentiation goes first. We figure out what is x to power of 4 and then we multiply by 2. Notice the difference in the result. This is 2, that's a 16. And so let's do another one. Suppose I write minus x to power of 4. Again, that means minus x times minus x times minus x times another minus x. Since we have even number of minuses, it becomes plus and then x to power of 4. On the other hand, if I had written minus x to power of 4, that meant minus x to power of 4. That is, you figure out what is x to power of 4 and you make it negative. Notice in this case we have positive, in this case we have negative, and so on. It's important to remember this sequence: parentheses, exponentiation, multiplication, division, addition, subtraction. If you have multiple parentheses, then you go from the innermost parentheses 2, and you work your way to the outermost parentheses. If you have exponentiation without any parentheses, you start from, there are several of them stacked on top of each other, you start from the very top and then you work your way to the bottom. If you have several multiplication and addition without the parentheses, the way to carry it out is from left to right, as you are accustomed to. Also, if you have several addition and subtraction without any parentheses, again you carry that out from left to right. So these are ways of breaking ties between possible interpretation of an expression, and we want to be careful with this. The most common error that the student make is in this situation, what is meant by minus. So if I write like minus 5 squared, what does that mean? That means minus 25. Does minus get squared? No, it doesn't. If it was minus 5, the whole thing in a parentheses, then I would have understood that I am multiplying this thing by itself twice, and that would have been plus 25. So when we are dealing with polynomials and powers, some of them with positive multiple, some of them negative multiple, we have to be careful about what these things mean and how to interpret them. So let's state a very important rule that we keep using, which is the distributive law. If you have a number times the sum of two other numbers, then you can carry out individual multiplication and then add them up. Here is another version that comes up quite often. What if I have a plus b times c plus d? We can use this property twice and find out what this is going to be, but let me explain it in a way that perhaps is memorable. Suppose you have a rectangular piece of land, and it is divided into 4 pieces. So suppose the length of this side is A, and this is B, and this is C, and this is D. Now if we want to find out the overall area of this, of course I can add this to length and these two, so I'll have A plus B for perhaps the height, C plus D plus for the length, and I multiply these two and find the area. But there's also another way of finding it out, which is finding each of these pieces and then adding them up. So if I have A and C, this area will be AC. This one will be AD. This one is going to be BC, and this one is going to be BD. So this area is made out of these 4 pieces. I write it AC plus AD plus BC plus BD. Probably you have learned this thing in your algebra class as foiling method. However you do that, just be careful that you are multiplying all the terms of the first parentheses with all the terms of the second parentheses. So if you have several items that are added to each other, each group in its own parentheses, to multiply them we have to use this rule. One of the exercises that comes up in the context of that optimal box we talked about looks like the following, or has the following component to it. Suppose I make an example, say 5 minus 2x times 8 minus 2x. So 5 and 8 has to be multiplied, 5 times 8. Then 5 and minus 2x. So I'll have 5 times minus 2x plus minus 2x times 8. So this is minus 2x times 8, and finally I have minus 2x with this other minus 2x, minus 2x times minus 2x. Now I simplify. 5 times 8 is 40. 5 times minus 2x is minus 10x. Minus 2x times 8 is minus 16x. Minus 2x times minus 2x. Minus 2 times minus 2 is 4. X times x is x squared. We simplify to 40 minus 26x plus 4x squared. Notice that I wrote this thing in a proper order. There's no x's here, or x to the power of 0 is here, x to the power of 1 is here, x to the power of 2 is here. Another common way of doing this thing is to start from high exponent and go to low exponent. So that is standard way of writing a polynomial. So we ended up with this polynomial. We practiced how to do foiling and how to simplify this. Now, interesting thing is that all of this comes up in the context of making an optimal box. So that was the promised topic here. We said we are going to see what does all of this algebra have to do with aspects of real life. Making a simple box brings us the issues that we are talking about right now, and more advanced issues, in fact, that we are going to be dealing with later on. Okay, now we want to prepare ourselves for this issue of making an optimal box. We said we can make a very simple box from a cardboard, a sheet of a rectangular piece of cardboard. We take some small squares from the corners, identical squares. We cut them out and fold on the dotted line and make a box. There's no top for this box, it's just the bottom portion. The question is, how big should this square be so that we get the best box? What do we mean by the best box? Perhaps what we have in mind is how much we can stuff in that box. That is, what's the volume of that box? Now I'm going to show a little demo of this problem, and then we are going to open it up in the next lecture and dig in and see what happens there. So here's a nice website, GeoGebra. People do a lot of mathematics here. So I'm using John Albright's work related to the exact same issue. So here is our cardboard. You can decide on the size of this cardboard by making it bigger or smaller, taller or shorter, and whatever you want. So let me go back to what I had here. Now we want to decide how much to cut from each corner. So you control it here. So here I go ahead and designate, perhaps here I'm going to cut one of the squares, perhaps two, and so on. Well, once you cut this thing, or at least cut a portion of this thing, what do? Well, you are going to take these flaps and then fold them. So here you can see I'm going to fold them. So we did the cutting. On the dotted line we go and fold this thing and we make a box this way. In practice they leave these squares dangling so that you can actually staple them to this size. I still remember boxes made in this style when I was a kid, and it would be okay for light objects like candy and such. It would be okay. So as we make this box at the end, well, now we have a completed box. The question is, well, how much candy I can put in this? And the issue is, well, it depends on the volume. typically you want to make a box with the biggest volume that you can have from the original cardboard. So the issue becomes, how much should I cut? Should I cut 1 square, 2 squares, 3 squares? Can't go too high up, because if you go all the way up, there's nothing left of the box. There's no volume left. At the end, at the other extreme, if you don't cut anything at all, well, you just have a sheet of cardboard, and of course you can't use that as a box either. So at these two extremes, at the very beginning, smallest cut or the largest cut, we can't fit anything in the box. The question is, where is that sweet spot? How much should I cut to get the best that I can have? And we are going to see all the things that we learned from polynomials is going to come in to set up the problem. And later on, there's going to be a topic that we are going to talk about. It's called differentiation. That's going to help us to figure out what is the optimal box. So that is for the next lecture. So in the process, we are going to see that polynomials of this type are going to come in, and we need to graph them and figure out what's the high and low of it, and so on. So that's going to be for our next lecture. Until that time, good luck and God bless.